partial derivatives. We want to give the definition for the partial derivative and then use the formula for derivatives after that to be able to compute whether it's the first or second partial derivative. Look at some of the properties of partial derivatives in this section. First, we begin with the definition for partial derivatives of a function of two variables. Let me scroll down. We could talk about the partial derivative of the function f xy with respect to x. And what it does is it takes the limit of the function, but it looks at the change of x, but it treats y as a constant or coefficient. So y is fixed. So we look at the change of f with respect to x, and then it's a ratio divided by the change of x itself. Or we could talk about the partial derivative of the function f with respect to y. And so this becomes the limit as delta y goes to 0. Here we treat x as a constant or coefficient. X is fixed. And then now we look at the change of y with respect to z divided by the change of y itself, a ratio. So two slopes, then taking the limit, and we get the idea of the derivative. We say that these partial derivatives exist if their limits exist. So the partial derivative exists because it's a direct implication of the limit itself. Well, we can take the idea of that definition for the limit or for the partial derivatives, and we can work some problems making use of that. Here on this page, it's just some notations that we use for the partial derivative. So if you see these symbols here, it still represents the partial derivative of f with respect to x. Since f of xy is equal to z, we can say z subscript z, subscript x, that is, or the partial of z over the partial of x, or the partial of z with respect to x. If you want to evaluate the partial derivative, so we could talk about the evaluation of the partial derivative of z at a point a comma b, which is the same thing as f sub x, that is the partial of f with respect to x at a comma b. We could talk about the second derivative, third derivatives, partial derivatives, if you will. So here, the so-called higher order partial derivatives. The first one, differentiate twice with respect to x, and so that's the notation that we can use. So this is the partial with respect to x on the partial of f with respect to x, and you can write that as the second partial of f with respect to x. Likewise with y, the partial of y on the partial of f with respect to y, or the second partial of f with respect to y. We can talk about the mixed partial derivatives. Here, this is the partial of y on the partial of f with respect to x. Now, I better note this. This is important in terms of the order, which is actually being done first. The term that's in the parentheses is actually being applied first. So here, this is the partial of f with respect to x. I take that result for number one, and then take the partial of that result with respect to x. For number two, what's in parentheses, first is what I do. I take the partial of f with respect to y, and then on that result, I take the partial of that with respect to y. Number three, first here, Because this is in parentheses, we take the partial of f with respect to x, and then on that result, take the partial with respect to y. Okay? So that's what this notation means. Now, the interesting thing, let's go down to number 4, is that the mixed partials, the mixed here second derivative partials, are the same. So numbers 3 and 4, here we have symmetry with respect to the second partial derivatives. And we have a problem or two that illustrates that. And they ask you to find those second partial derivatives and then look at the partial of f(x,y) and the partial of yx, excuse me. And then you want to see if they're the same. And they will be. So. Well, let's look at some problems. Again, equality of the mixed partial derivatives. So first, here it says find both first partial derivatives. So we find the partial of z with respect to x. So what that means is that I treat all the other variables as constants or coefficients. So this becomes 6 minus 12xy pardon me? Excuse me, I'm sorry. 2xy. Actually, I'm thinking about something. There's a problem that I don't see that should be here. Maybe it's somewhere else. 6 minus 2xy. Okay? Then what about the partial of z with respect to y? So x here is a constant or coefficient, so I go to this next term on the negative x squared y. That becomes negative x squared plus 16y. Is that all right? Okay. So what about this one? And again, you know, you can write this as the partial of z with respect to x. Same thing as saying here z subscript x. So we take the partial of z with respect to x. This is 2y squared. That's the coefficient. Now times this derivative of the square root of x. This is 1/2 times x to the negative 1/2 power, and you can write that as y squared over the square root of x. What about the partial of z with respect to y? Well, that's just 4y times the square root of x. Are you with me? Okay. Yes, sir. Pardon me? What's the derivative of the square root of x? Right. So take the partial of z with respect to x. This becomes 1 over x squared plus y squared. Now times the derivative of x squared plus y squared with respect to x, that's just 2x. So this is just 2x over x squared plus y squared. Now do you see that the natural log of x squared plus y squared is symmetric? X squared plus y squared? Do you see that? If you do, then the partial of z with respect to y is 2y over x squared plus y squared. Are you with me? Okay. Partial of z with respect to x. We use the quotient rule. It's the derivative of the numerator with respect to x. That's just y times our denominator minus our numerator times our denominator, its derivative, with respect to x. So that's just 2x. And that's all over x squared plus y squared to be squared. We can clean that up. So this is x squared y plus y to the third minus 2x squared y all over x squared plus y squared to the second. And that just gives us y to the third minus x squared y over x squared plus y squared to the second power. Now just looking at this, looking at the partial of z with respect to x, what's the partial of z with respect to y without working it out? X to the third minus y squared x over x squared plus y squared to the second. Go back and look at z. It's x times y, right? All over x squared plus y squared. Again, that guy is symmetric too in its form. Now, when you see that, it just saves you on some time. If you notice that they're symmetric. Now this guy would not be symmetric if you had z equal to x over x squared plus y squared. See that? That guy is not symmetric. So the partial of z with respect to x here would have a different form than the partial of z with respect to y. But when you have something like z equal to x squared y squared over the square root of x times y, that's symmetric. See that? See how that form is? If you had something like z equal to the square root of xy, if I find the partial of z with respect to x, the form for the partial of z with respect to y is going to be very similar. I just transpose the x and the y. So I'll do one more, then I'll give you one to do. So the partial of here of z with respect to x, this is negative sine of xy times the derivative of xy with respect to x, that's just y. And I better write it correctly. This is negative y, so we don't get confused with that y on the back there. So now the partial of z with respect to y, again, x times y, that would be symmetric. So I would assume that the result should be negative x times sine of xy. All right, well, let's see. This is negative sine xy times the derivative of xy with respect to y, that's just x. So we write that as negative x times sine of xy. Okay? You try that one. Now finding that second one should be easy, right? You do the work on the first one. Okay, so the partial of z with respect to x, you get x over the square root of x squared plus y squared. Right? You get 1/2, but then you take the derivative of the inside, that's 2x, right? So the 1/2 times 2 goes out. Okay. And this second one has the same form. It's just y over the square root of x squared plus y squared. Okay. Everybody with me? Okay. Good. Here we have a function f, and it depends on 3 variables, x, y, and z. So we find here the partial derivatives. Here we call f of x, y, z w. So we find the partial of w with respect to x. Now I use shorthand when I write these terms. You know, all the way through, you should be writing parentheses x, y, z, but I use the shorthand. So this is the same thing as in the partial of w with respect to x. So this is 6xy minus 5yz. Is that what you got too? So what about the partial of w with respect to y? 3x squared minus 5xz. I have a y over there at that last part, so that's 10z squared. Again, the correct way to write all that out is the partial evaluated at the point x, y, z. I use the shorthand. What's the shorthand? The partial of w, say for example, with respect to z. Well, for that first term here, there's no z there, so that's treated as a constant. There's a z over here, so this is negative 5xy, plus that becomes 10 times 2, or 20 yz. Is everybody happy with that? Okay. Good deal. Okay, you do that one. Is x squared plus y squared and z squared, are they symmetric? You better believe it. So once you find that first one, the second and third one should be easy to get. All right. What'd you get? Right. So you get x all over the square root Then for the partial of w with respect to y has that same form. That's just y over the square root. The partial of w with respect to z, same format. Okay. Is everybody good with that? Good. Find all values of x and y such that the partial of f with respect to x is equal to 0. You set that equal to 0, and then the partial of f with respect to y is set to equal to 0 simultaneously. So once you do that, then after that, find the values of x and y that satisfy that. So first we find the partial of f with respect to x. This is 2x plus y minus 2. Here they say set it equal to 0. Find the partial of f with respect to y. This is x plus 2y plus 2. That's set to equal to 0. Now if you look at the system that you have, this is a linear system. This is 2x plus y is equal to 2. And this is x plus 2y is equal to negative 2. You just solve that system. So if I take the first equation and solve for y, I get y is equal to 2 minus 2x. I take y equal to 2 minus 2x, you remember, and plug that into the second equation for y. Substitute that. So I get x plus 2 times y, 2 minus 2x. That's equal to negative 2. Solve for x here. X plus 4 minus 4x is equal to negative 2. So here we get negative 3x is equal to negative 6. X is equal to 2. If x is equal to 2, I plug that in for y, and I get y is equal to 2 minus 2 times 2, so I get negative 2 for y. So it's said to find all values of x and y such that their first partial derivatives are set to equal to 0. And when you do that, you get x equal to 2, y equal to negative 2. Is that straightforward? You remember solving system of equations. That's all you do. There's other ways you can do that, but that's, I think, the simplest. Call that substitution. Yes, sir. Yes. You find one and you know the other if the equation is symmetric. Yes, sir. Yep. Save you on some time. Okay, you do this one. What'd you get, Jackson? Yes. Said find all values of x and y. Yep. And then what you get for y? Thank you. Looking at my papers, maybe I got it wrong. I'd work them fast. So, yes, I get y equal to 1. Bro Lewis, you got it? Yeah? Did you get x? What'd you get for x? Okay. I use y is equal to 2x minus 5, right? Y is equal to 2x minus 5. If you get x equal to 3, you plug in x equal to 3. 2 times 3 is 6, minus 5 is 1. Brother Donnie? Sir? X equal to 3 and y equal to 1. Is everybody okay with that? Okay. Here, find the 4 second partial derivatives and then observe that the second mixed partials are equal. So here we find the partial of z with respect to x. This is 4x to the third minus 2y. Find now the partial of x, the partial of z with respect to x twice. So the second partial of z with respect to x, if you will. So this is 12x squared. What about the partial of z with respect to x, then y? So for this one, this guy works off of the partial of z with respect to x. On that guy, I find now its partial with respect to y. That just gives you minus 2, indeed. About the partial of z with respect to y now. So this is negative 2x plus 9y squared. Partial of z with respect to y twice, or the second partial of z with respect to y, if you will. So this is 18y. Then the partial of z with respect to x, then y. So this is acting off of, sorry, I got that wrong. This should be yx. So I look at the partial of z with respect to y, and then I take the partial of that result with respect to x. See, you get -2. And so these two are supposed to be the same. Then they asked to find, you want 4 of them, and these are the 4 that they're talking about. Okay. Then let me give you one to do and see if you can do that same thing, okay? Try your hand at that. Got it. You got it, Donnie? What'd you get for the mixed second partials? Yes. Should be what, -12xy? Right. Go back and check that. The mixed partial comes off of either the partial of z with respect to x, then take that partial with respect to y. Okay, so you got it? So the second partial of z with respect to x Does everybody get that for that second partial of z with respect to x? And then the second partial of z with respect to y. (12y squared). Then the mixed partial, they came out to be the same. (-12xy). Which one? Z, y, y. Yes, yes. That's negative 6x squared plus 12y squared. Yeah. Yes, sir. Hmm. This guy, remember, this comes off of, let me write it. This is the partial with respect to y of the partial of z with respect to x. You find what's in the parentheses first. So you find the partial of z with respect to x. And this gave you 4x to the third minus 6x y squared, right? So now here's what this guy says. This is the partial with respect to y on 4x to the third minus 6x y squared. So you find this partial with respect to y. Won't that be negative 6 times x times this y squared becomes 2y, so that's 2 times negative 6. You get negative 12xy, right? Okay. Yes, sir. All right. Any other questions? Right here? Yes, sir. This says this is the partial with respect to y on the partial of z with respect to x. So what's in parentheses, you compute that first. So you take the partial of z with respect to x, and then which we got here, and then now on this, we apply this operator on it. Now once I get the partial of z with respect to x, now take the partial with respect to y. Right. Okay. Is that all right? Okay, good. For some reason, there was the problem from the previous section that led into this section, and there was a problem that should have been the first one that we worked, but I didn't even put it in my notes here, and I don't know why. I can give you what it is. F of xy is equal to, let's say, x squared times y. We did this in the previous section, but this is the section that we were trying to get to. That is, find the partial of f with respect to x at xy, which is the limit as delta x goes to 0 of f of x plus delta x comma y minus f of x y all over delta x. Didn't we do one like that on Tuesday? Yeah. It was the last one we did, indeed. So if this is the case, right, so this is the partial of f with respect to x at the point x comma y is the limit as delta x goes to 0 of x plus delta x to be squared times y minus x squared y over delta x. So here we get the limit as delta x goes to 0 of x squared y plus 2x delta x y plus delta x squared y minus x squared y all over delta x. The x squared y's cancel. You have the limit as delta x goes to 0 of 2x y plus delta x y parentheses just fracted out delta x divided by delta x, because the delta x divided by delta x cancels out. So I have the limit as delta x goes to 0 of 2xy plus y delta x. As delta x goes to 0, that just have 2xy, right? So, but you see, if I have this function x squared y, and then you say find the partial of f with respect to y, the short version is you look at that and take the derivative with respect to x and treat that y as a coefficient. That's just 2xy. Right? So on the test, I will ask you to find the partial derivative by definition. This is the definition. If you try to, when I ask you that, you give me that shortcut answer, I'm going to mark it wrong, right? Because I will say solve by definition. Right? I will have others on there where you can just use the shortcut and just get the partial derivative. That's fine. I'll give you a few of those, but I will have one very similar to this. Okay? Let's take a break. Take a 5-minute break and we'll come back and look at the next section.